Today we're going to talk a little bit more about logarithms and logarithmic functions. So first off, we're going to talk about the exponential form of an equation. So y equals b to the x. We talked about this yesterday. This is called the exponential form. If we were to find the inverse of this, the first thing we would do is switch our x's and y's. So we have x equals b to the y. And then we need to solve for y. We remember from yesterday that we can write this in logarithmic form. So log base b of x equals our exponent, y. So now we have the inverse of our exponential form. And you'll notice that the inverse of our exponential form is our logarithmic form. So we know that these are inverses. Now if two functions are inverses of each other, that means f of g of x is equal to x. So we have f of x as our first function, so we're going to call our second function, our logarithmic function, g of x. So if we take f of g of x, we simply plug our g of x in for x in our first equation. So we get b to the log base b of x. And we know that that has to equal x because that's a property of logarithms. So now we know this property of logarithms is true. So if we have a base to the logarithm of the same base of a number, the answer is just that number. It's almost like these cancel each other out. If f of g of x equals x, we also know that g of f of x has to equal x because they're inverses. So we can plug f of x in for our x in our logarithmic function. So log base b, and now we're going to plug in f of x here. So of b to the x has to equal x. This is another property of logarithms. Basically, it's as if these cancel out and we're left with just our x. Now we're going to do this with numbers. So 8 to the power log base 8 of x, once again, we know from our properties that these essentially cancel out, and this just equals x. Over here, once again, we know from our properties, log to the base of a number of that number to a power just equals the power. So we know that this just equals negative 3x. Now this one, there's nothing that we notice immediately that cancels out, but we can rewrite 64 as 2 to the 6th. Now remember, when we do power to power, we multiply, so we simply have log base 2 of 2 to the 6x. It's as if these cancel out, and we're left with 6x, based on our properties. With this one, it's easiest if we rewrite natural log as log base e, because that's what natural log is. Now, we can see that these, obviously, cancel out, and we're left with just 20. Now we're going to find the inverse of trig functions. Not trig functions, logarithmic functions. In order to do that, the first thing we're going to do is switch our x and y. So we have x equals log base 8 of y. Now we need to solve this for y. So to solve this, we can switch this to exponential form. This can be rewritten as 8 to the x equals y. And so now we have our inverse. We can do the same thing down here. So the first thing we want to do is switch our x's and y's. So x equals 0.4 to the y. Now we need to get y equals. That's our goal. In order to do this, we can switch this to logarithmic form. So log base 0.4 of x equals y. And that's our inverse function. Once again, over here we can switch our x's and our y's. Now, in order to get y by itself and get it out of the exponent, we're going to need to switch this to logarithmic form again. So that's just log base e of x equals y plus 2. We can rewrite log base e as the natural log of x, and then to get y by itself, we simply subtract 2 from both sides. So y equals the natural log of x minus 2. Here we're going to switch our x's and our y's, so x equals the natural log of y plus 1. Now I think it's easier if we rewrite this as x equals log base e, because that's what our natural log is, of y plus 1. So we can rewrite this in exponential form. So we have e to the x equals y plus 1. So to solve for y, we simply subtract 1. E to the x minus 1 equals y. And so that's our inverse. Now we're going to use our inverses in order to graph, and then we're going to find the domain and range. So we don't know how to graph log base 7 of x, but what we do know is how to find the inverse. And if we can find the inverse and create a table of values, we can find the original graph. So we're going to start by rewriting this as y equals log base 7 of x. Now to find the inverse, we switch our x's and y's. Now we can write this in exponential form. So 7 to the x equals y. This is something we're familiar with, and so we can easily find a table of values in order to find our points x and y. So if we use x equals -1, 7 to the -1 is 1/7. If we use 0, 7 to the 0 is 1. If we use 1, 7 to the first power is 7. If we use 2, 7 squared is 49. Now, this is a table of values for our inverse function. But we don't want to graph our inverse function. We want to graph our log function. Well, in order to graph the inverse of a function, you simply switch the x and y values. So at this point, on our graph of our log function, instead of being -1, 1/7, would simply be 1/7, -1. This point would be 1, 0. This point would be 7, 1. And this point would be 49, 2. Right, we simply just switch our y and x values. So now if we were to graph this, we would do the point 1/7, -1, 1, 0, 7, 1, and obviously our point 49, 2 would be much farther off the graph. This is never going to actually touch the y-axis. It's just going to get closer and closer to it. And that's because in our original table of values, we know that it can't, or in our table of values for our inverse, we know that no x will ever give us a negative y. And so when we flip it, we know that we're never going to have a negative x. So it's never going to cross over the y-axis. So when we go to identify the domain, our domain is x is greater than 0. So we're never going to have a negative x. And then our range is simply all real numbers. Once again, we don't know how to graph this logarithmic function, so we can find the inverse. We're going to switch our x's and y's. So x of log base 1/4 of y. And then in order to solve this, we're going to switch it to exponential form. So 1/4 to the x equals y. We can do our table of values. If x equals 0, y equals 1. If x equals 1, y equals 1/4. If x equals -1, y equals 4. If x equals -2, y equals 16. Once again, this is for our inverse function, and we want to graph our log function. So we're going to have to switch our x's and y's. So the log function would have the points 1, 0, 1/4, 1, 4, -1, and 16, -2. So we can graph that. 1, 0, 1/4, 1, 4, -1, and 16, -2, which would be way over there. So we know, pardon my smartboard graph, we know that that line's going to get closer and closer to y without ever touching it, and it's going to go on forever the other direction. So we know that our domain is all x greater than 0, and we know that our range is all real numbers.